in December of the year 1972, an astronaut named Eugene Cernan slowly climbed up the metal ladder of the lunar module Challenger. He paused, looked back at the grey dust, and became the absolute last human being to ever stand on the surface of another celestial body. Since that historic, fleeting moment, more than half a century has slowly passed. Over those long decades, humanity has ambitiously sent dozens of robotic probes, orbiters, and rovers into the deep dark, aiming for the red planet known as Mars, and the terrifying, sobering reality is that approximately half of them completely failed to achieve their mission. They violently crashed into the rocky surface, permanently lost communication in the cold void, or simply vanished without a single trace into the thin, dusty Martian atmosphere. Every single successful rover, every landing module that survived the brutal descent, and every orbiting probe has sent back mountains of crucial data to Earth. And this slowly accumulating data has painted a picture of the fourth planet from the Sun that is significantly more complex and significantly less hospitable than the early space enthusiasts ever dared to imagine in the 1960s. Mars is absolutely not a second home for humanity. It is not even a suitable place for a temporary stay, not in the way that the frozen deserts of Antarctica or the crushing depths of the deep ocean are suitable. Mars is a hostile, unforgiving, and deadly wasteland, and truly understanding this dark reality requires a very careful, terrifying look at the physical, biological, technological, and psychological limitations that will make the very first manned mission to Mars not a glorious triumph of the human spirit, but quite possibly a horrific, predictable tragedy with an outcome we already know. Hello, and welcome to This Is Space. I am Christopher, your guide through the infinite dark. If you enjoy these deep atmospheric explorations into the unknown cosmos, please consider subscribing to the channel and leaving a comment below. Your support allows us to keep venturing further into the deep mysteries of the universe, peeling back the layers of reality one by one. Let us begin by confronting the sheer, tyrannical scale of the distance involved. The physical space between Earth and Mars constantly, wildly varies from roughly 55 million kilometers at their absolute closest approach to over 400 million kilometers when the two planets are positioned on completely opposite sides of the burning sun. This incredibly vast astronomical distance fundamentally dictates absolutely everything about a potential mission. Using our current modern chemical rocket engines, a one-way flight to the red planet will take anywhere from 6 to 9 agonizing months of drifting through the empty dark. But the sheer travel time is only a small part of the terror. The true horror lies in the fundamental impossibility of immediate operational help. A radio signal, which travels at the absolute maximum speed of light, takes anywhere from 3 to 22 agonizing minutes just to cross the vast void between the two worlds. This means that a single desperate cry for help from a dying astronaut will take up to 22 minutes to reach mission control on Earth, and any possible instructions or advice will take another 22 minutes to return. That is a total communication delay of up to 44 terrifying minutes just to get an answer to a single question. When the brave Apollo astronauts experienced a catastrophic explosion on board Apollo 13, the dedicated ground control team in Houston could communicate with them and analyze telemetry almost in real time, saving their lives. On Mars, that exact scenario is completely, physically impossible. Any sudden accident, any unexpected failure of a critical life support system, any sudden medical emergency will strictly require the isolated, terrified crew to make completely autonomous, life or death decisions with extremely limited resources, incomplete technical information, and absolutely no possibility of receiving spare parts or an emergency medical evacuation. History shows us exactly how easily things go wrong in the vacuum of space. In January of 1969, the Soyuz 5 spacecraft failed to separate properly, causing Boris Volynov to endure a terrifying, uncontrolled re-entry where the heat melted the door seals. In 1997, a cargo ship violently crashed into the Mir space station, depressurizing the module. In 2007, toxic ammonia leaked into the International Space Station. Every single time humans have survived these disasters, it was because Earth was right there to actively save them, to analyze the data, and to provide immediate, brilliant solutions. On Mars, Earth will just be a silent, pale blue dot in the sky, completely incapable of helping. The crew will be entirely on their own. The very atmosphere of Mars is a silent, invisible killer. It is composed predominantly of toxic carbon dioxide, making up roughly 95% of its total volume, with only tiny trace amounts of nitrogen, argon, and virtually no usable oxygen. But the toxic composition is not the most immediate, violent threat. The atmospheric pressure on the surface of Mars fluctuates between 600 and 1000 pascals. That is less than 1% of the atmospheric pressure we comfortably experience at sea level on Earth. If a human being were to suddenly find themselves exposed to the Martian environment without a pressurized spacesuit, they would completely die in a matter of seconds, and they would not just peacefully suffocate from a lack of oxygen. The extremely low atmospheric pressure would cause the liquid water in their bodily tissues to violently vaporize. The moisture in their lungs would instantly turn to expanding steam. The vital blood flowing through their peripheral capillaries would aggressively boil and expand, a horrific physical process known as ebullism. Absolute unconsciousness would violently set in within approximately 15 short seconds, followed rapidly by irreversible brain damage and death. Experiments conducted in the 1960s showed that animals exposed to these exact pressures suffered catastrophic biological failure in less than a minute. This terrifying physical reality means that any accidental tear in a spacesuit, any micrometeoroid puncturing the thin hull of a habitat module, or any failure of a simple airlock seal leaves the astronauts with only seconds to react before their own bodily fluids betray them. The temperature on Mars presents another massive, systemic threat to human survival and mechanical reliability. The average temperature on the dusty surface is a freezing -60 degrees Celsius. However, the lack of a thick atmosphere means that temperatures swing violently and unpredictably. Near the Martian equator, a summer day might briefly reach a comfortable 20 degrees Celsius. But as soon as the sun dips below the horizon, the heat instantly vanishes into space, and the temperature plummets to -80 degrees. In the dark polar regions, the brutal winter temperatures drop to a staggering -140 degrees Celsius. It gets so unbelievably cold that the carbon dioxide in the thin atmosphere actually freezes solid and falls to the ground as dry ice snow. These extreme, violent temperature fluctuations place an enormous destructive physical strain on absolutely any technical equipment designed to keep fragile humans alive. Space-grade materials suffer from severe thermal fatigue due to the constant, daily expansion and contraction. Rubber seals and critical gaskets lose their elasticity and eventually crack. Sensitive electronic components are pushed far beyond their safe operating limits. Vital lubricants thicken and crystallize, causing moving parts to completely seize up and break. The robotic rovers currently on Mars have constantly struggled with these thermal extremes, and they were specifically built to endure conditions that would instantly kill a human. A life support system simply cannot be allowed to fail or freeze, not even for a single hour, or the entire crew will perish. But the most insidious, unavoidable killer on Mars is completely invisible. In deep interplanetary space, and on the Martian surface, represents arguably the most severe, unsolvable long-term threat to the health of any human crew. On our safe, comfortable Earth, we are heavily protected from cosmic radiation by a massive, invisible magnetic field generated by the spinning, liquid iron core of our planet, as well as a thick, dense atmosphere that acts as a physical shield. Mars completely lost its protective magnetic field roughly 4 billion years ago, and its atmosphere is far too thin to stop anything meaningful. The astronauts will be completely, violently exposed to radiation from every single direction. The radiation detectors on the Curiosity rover revealed that the annual dose on the surface of Mars is roughly 0.67 sieverts. That is 20 to 30 times higher than the absolute maximum allowed dose for nuclear power plant workers on Earth. And during the long, dark transit through deep space, the doses will be even higher. The crew will face two distinct, deadly forms of cosmic radiation. The first is galactic cosmic rays. These are heavy, highly energetic atomic nuclei that have been violently accelerated to nearly the speed of light by catastrophic supernovae explosions deep in the cosmos. These heavy destructive particles, specifically heavy ions like iron and nickel, possess immense penetrating power. When one of these heavy cosmic bullets passes directly through human tissue, it leaves a microscopic path of absolute destruction, shattering fragile cells, permanently mutating DNA strands, and ionizing vital molecules. Traditional radiation shielding, like thin layers of lead or aluminum, is practically useless against these massive cosmic rays. In fact, when these heavy rays strike a metal shield, they shatter the metal atoms, creating a deadly secondary shower of cascading radiation that can actually increase the total biological dose the astronauts receive. The only truly effective shield is several meters of solid water or dense plastic, which is far too heavy to ever launch on a rocket. The second invisible radiation threat comes directly from our own sun. Solar energetic particles are violently blasted outward during unpredictable solar flares and coronal mass ejections. While they are generally less energetic than the galactic rays, a sudden solar storm can increase the radiation level by orders of magnitude in a matter of hours. A powerful solar flare, like the one that occurred between the Apollo 16 and Apollo 17 missions in August of 1972, could easily cause acute radiation sickness, severe vomiting, cellular collapse, and a horrific, painful death within days if the crew is caught outside without incredibly thick shielding. Even inside a heavily shielded module, the long-term continuous exposure to this radiation environment is deeply devastating. It significantly increases the risk of aggressive, untreatable cancers forming anywhere in the body. But far worse, advanced experiments have shown that this specific type of heavy particle radiation causes severe, irreversible damage to the central nervous system. It accelerates the aging of the brain, causing severe cognitive decline, violent mood swings, memory loss, and neurological symptoms closely resembling early-onset Alzheimer's disease. The brave, highly trained astronauts who leave Earth with brilliant, sharp minds might arrive at Mars confused, paranoid, deeply forgetful, and completely incapable of executing complex, necessary survival tasks. As we drift deeper into the harsh realities of interplanetary survival, take a moment to subscribe to This is Space, and let us know your thoughts in the comments. Do you think the human body is simply too fragile to ever conquer the stars? Let us discuss it below. Even if they somehow miraculously survive the invisible radiation and the boiling vacuum, the sheer lack of gravity will slowly, systematically destroy their bodies from the inside out. The human body evolved over millions of years to constantly, relentlessly fight against the steady, heavy pull of the gravity of Earth. Taking that physical gravity away during a 6 to 9 month journey through the void triggers a catastrophic cascade of biological failures. Without the constant mechanical stress of walking, lifting, and standing, the human skeleton actively begins to dissolve. The body reabsorbs the calcium from the unused bones, and bone density drops at a terrifying rate of 1 to 2% every single month. This bone loss is especially severe in the weight-bearing areas like the spine, the pelvis, and the massive femur bones. By the time they finally reach Mars, an astronaut could easily lose up to 15% of their total bone mass, developing severe, irreversible osteoporosis. Their bones will become fragile and porous, highly prone to shattering under the slightest physical impact. At the exact same time, their muscles, especially the critical anti-gravity muscles in the back, glutes, and legs that maintain human posture, will atrophy and aggressively shrink. Despite exercising exhaustingly for hours every single day on complex resistance machines, a process that is mandatory on the space station, they will still lose up to 20% of their muscle mass. They will arrive in Martian orbit incredibly weak. When they finally land, they will experience a planetary gravity that is only 38% of what they are used to. To a healthy human on Earth, that might sound like a fun, bouncy experience, but to a weakened, sick, bone-depleted astronaut who has been floating in a cramped tube for 9 months, simply standing up in a heavy, pressurized spacesuit will be an exhausting, dangerous ordeal. A simple trip and fall while stepping out of the lander could easily result in a shattered femur or a broken spine. On Earth, these are manageable injuries. On a desolate planet with 0 hospitals, 0 blood banks, and 0 advanced surgical capabilities, a broken bone will be an absolute agonizing death sentence. Furthermore, without the gravity of Earth, constantly pulling bodily fluids down into the legs, those fluids violently shift upward into the chest and head. This dangerously increases the pressure inside the human skull and completely crushes the delicate optic nerve. This specific medical phenomenon, known as flight-associated neuroocular syndrome, has been thoroughly documented in astronauts returning from long stays on the space station. Many astronauts return with permanently blurred vision, flattened eyeballs, and folds in their retinas. The exact biological mechanisms are still not fully understood, and there are absolutely no known preventative treatments. In the deep isolation of Mars, where seeing clearly is a matter of life and death, losing your eyesight could easily mean making a fatal mistake while repairing a microscopic life support valve or misreading a critical atmospheric gauge. The human immune system also fundamentally changes and degrades dark matter of space. The activity of vital T cells plummets, and the delicate human microbiome falls out of balance. Simultaneously, latent viruses hiding dormant in the human body, such as the herpes virus, violently reactivate due to the immense stress. Bacteria actually become more virulent and highly resistant to antibiotics when grown in microgravity. A closed, highly recycled environment like a spaceship or a Martian habitat is the absolute perfect breeding ground for a catastrophic infectious epidemic. A single mutated bacterial strain spreading through the ventilation system could easily incapacitate the entire crew simultaneously, leaving absolutely no one awake to monitor the failing life support machines. The psychological horror of this mission is almost impossible to truly overstate. Imagine being permanently trapped inside a small, noisy, metallic cylinder for years, completely surrounded by the exact same small group of stressed, exhausted, and terrified people. You cannot ever open a window to breathe fresh air. You cannot feel the wind on your face or the sun on your skin. You cannot smell rain, fresh earth, or growing plants. You are permanently separated from every single human being you have ever known, and every single thing you have ever loved, by hundreds of millions of miles of empty, dark void. Earth is no longer a world. It is just a tiny, fading, pale blue star in an endless black sky. Ground-based isolation experiments, such as the Mars 500 project conducted in the year 2010, have repeatedly shown that even highly trained, carefully selected professional volunteers eventually succumb to deep depression, severe anxiety, sleep disorders, and violent interpersonal conflicts when trapped together for long durations. And those volunteers knew they could open the door and walk out at any time. In the actual cold reality of a Mars mission, where every single minor mistake could result in the horrific death of the entire crew, the constant, unrelenting psychological stress will easily break minds. Deep paranoia will set in. Small, petty disagreements over food rations, sleep schedules, or daily tasks will quickly, inevitably escalate into dangerous, unresolvable hostilities. History is full of terrifying examples from isolated polar expeditions and early submarine voyages where extreme isolation drove men to violence and mutiny. On Mars, an unresolvable personal conflict could easily destroy the entire mission. The machines will absolutely fail. It is a mathematical certainty. The life support systems required to artificially keep humans alive in a dead vacuum are incredibly, maddeningly complex. They must constantly recycle toxic human urine and sweat back into pure drinking water. They must scrub deadly, exhaled carbon dioxide from the air and use heavy electrolysis to generate breathable oxygen. On the International Space Station, these vital systems break down completely multiple times a year. Valves stick, filters clog, and software glitches. They are only successfully repaired because replacement parts are constantly shipped up on regular cargo rockets directly from Earth. A Mars crew will have absolutely no resupply ships coming to save them. They must rely entirely, exclusively, on whatever spare parts they brought with them on launch day. When an oxygen generator inevitably shorts out, or a vital water pump seizes up from the constant wear and tear of a dusty environment, they must fix it themselves, or they will slowly, agonizingly suffocate or die of thirst in the dark. The current water recovery systems are only about 93% efficient. That missing 7% must be constantly replaced. A multi-year Mars mission would require systems that are practically 100% efficient, and such perfect technology simply does not exist anywhere on Earth. Furthermore, breathing recycled air for years means volatile organic compounds, off-gassing from plastics, electronics, and the humans themselves slowly build up in the confined atmosphere. The smell inside long-term space stations is famously described as chemically metallic and foul. The long-term health effects of breathing these toxic trace chemicals for years on end are completely unknown. Power generation on the red planet is another massive, critical vulnerability. Solar energy on Mars is incredibly weak, yielding less than half the power it does on Earth because the planet is so much farther from the Sun. Even worse, massive global Martian dust storms can completely block out the Sun for weeks, or even months at a time. This exact scenario killed the Opportunity rover in the year 2018, when its solar panels were completely buried in fine red dust. A human crew cannot simply go into hibernation mode and wait for the sun to return. They need massive, continuous power to heat the habitat, generate oxygen, and run the computers. Nuclear sources, like the small radioisotope generators used on rovers, do not produce nearly enough power for human life support. Compact nuclear fission reactors that could potentially power a colony are still entirely experimental and have absolutely never been tested in the brutal, unpredictable conditions of another planet. If the power dies on Mars, the heat dies, the air dies, and the crew dies shortly after. Growing food locally on Mars is a beautiful science fiction dream that shatters upon contact with reality. While hydroponics are possible, the energy required to simulate sunlight and grow enough calories to sustain a crew is astronomically high. Furthermore, the local Martian soil, known as regolith, is highly toxic. It is saturated with deadly perchlorates, chemicals that will destroy the human thyroid gland if ingested or inhaled. Before you could ever use Martian dirt to grow potatoes, you would have to thoroughly wash and chemically treat tons of it, a process requiring massive amounts of water and energy that the crew simply will not have. Extracting water from the deep underground Martian ice is equally problematic. It requires heavy drilling equipment, immense power to melt the ice, and complex chemical filtration systems to remove the heavy salts and toxins. And what about the fuel needed to simply return home? The entire architecture of modern Mars mission plans relies on a concept called in situ resource utilization, specifically using the Sabatier reaction to pull carbon dioxide from the Martian air and combine it with hydrogen from Martian water to create methane rocket fuel. This sounds elegant on paper, but this specific chemical process requires absolutely massive amounts of electricity and has never, ever been demonstrated on the industrial scale required to fill a massive interplanetary rocket. The fuel plant would have to be sent years in advance, operating flawlessly entirely on its own. If the automated fuel plant fails to produce the hundreds of tons of liquid methane required, the human crew will arrive on Mars only to realize they are completely, permanently stranded, gazing up at a sky they can never return to. The terrifying act of physically landing on the red planet is a completely unsolved engineering nightmare. The atmosphere of Mars is the absolute worst of both worlds. It is thick enough to create massive, deadly aerodynamic heating that will incinerate a spacecraft upon entry, but it is far too incredibly thin to actually slow down a heavy vehicle using parachutes. The heaviest object humanity has ever successfully landed on Mars is the Curiosity rover, which weighs roughly 1 single ton. To land a human habitat and an ascent vehicle, we would need to safely land modules weighing tens or hundreds of tons. This requires entirely unproven technologies like supersonic retropropulsion, firing massive rocket engines directly into the supersonic airstream while plummeting toward the ground. While companies like SpaceX have mastered landing rockets on Earth, doing it in the thin alien atmosphere of Mars with absolutely zero margin for error and zero chance of rescue is a completely different, terrifying gamble. Before we dive into the dark ethical implications of this mission, please remember to subscribe to This is Space. What technology do you think is the absolute most critical hurdle preventing us from reaching the stars? Let us know below. The specialized spacesuits required for Mars will have to be engineering miracles, and currently they do not exist. They must protect the fragile human body from a hard vacuum, deadly radiation, freezing temperatures, and highly abrasive, toxic dust, all while being flexible enough to allow astronauts to walk, bend over, and perform heavy manual labor for years on end. The suits currently used on the space station are designed exclusively for floating in zero gravity, not for walking on rocky terrain. The heavy suits used during the Apollo moon landings were only designed to last for a few short days. The fine electrostatically charged Martian dust will cling to absolutely everything. It will work its way into the joints of the suits, destroying the seals, tearing the fabrics, and eventually being dragged inside the living quarters. The Apollo astronauts suffered respiratory irritation just from a few days of breathing lunar dust. Long-term exposure to the toxic perchlorate dust of Mars could cause catastrophic, permanent lung damage to the entire crew. And when things break, which they absolutely will, the ability to repair them is virtually non-existent. You cannot bring a spare part for every single valve, wire, and computer chip. Advocates suggest using three-dimensional printers to manufacture spare parts on demand. While you can easily print a simple plastic wrench or a bracket, you absolutely cannot three-dimensionally print a highly complex microchip, a precision high-pressure seal, or a delicate medical instrument. Manufacturing complex electronics requires massive, pristine clean rooms and rare earth materials. Things that are utterly impossible to replicate inside a cramped tin can millions of miles from civilization. The medical reality of a Mars mission is a waking nightmare for any flight surgeon. It is fundamentally, physically impossible to anticipate and equip a spacecraft for every potential human medical emergency. Acute appendicitis, passing a kidney stone, a sudden massive heart attack, a debilitating stroke, or a severe blunt force trauma from an accident. Every single one of these common human conditions requires highly specialized, immediate medical intervention that is completely impossible to provide with limited resources. Conducting any form of open surgery in microgravity or partial gravity is chaotic and bloody. Blood does not pool neatly. It floats in the air as microscopic, deadly droplets that can be inhaled or short out electronics. Internal organs shift unpredictably. Even if you have a brilliant, world-class surgeon on board, their hands are tied without an entire hospital staff and heavy diagnostic equipment like MRI machines or CT scanners. The pharmaceuticals they bring will degrade much faster than on Earth due to the constant bombardment of cosmic radiation. Vital antibiotics and painkillers will literally lose their chemical potency before the mission is even halfway over, leaving the crew defenseless against infection and agony. Even a simple dental emergency, like an infected tooth root, which is a minor inconvenience on Earth, could cause unbearable, mission-ending suffering or a fatal systemic infection on Mars. The social and psychological structures required to keep a small group of humans sane and cooperative in a deadly environment are incredibly fragile. When human beings are completely isolated and utterly dependent on centralized, fragile technology for their very breath and water, the absolute conditions for extreme tyranny are created. Whoever controls the oxygen dial, the water ration, and the communication uplink effectively holds the power of a god over the rest of the crew. Democratic mechanisms, freedom of movement, and independent oversight simply cannot exist inside a closed environmental loop. Furthermore, the psychological toll of asynchronous communication cannot be ignored. The crew will receive video messages from their families on Earth, but they cannot have a conversation. They will learn of the deaths of their parents, the illnesses of their children, or the collapse of their home nations, and they will be completely, utterly powerless to do anything about it. They will suffer unimaginable grief in a tin can, entirely disconnected from the emotional synchronicity of human interaction. The legal status of the crew is also a massive unknown. If someone commits a murder out of sheer space madness, what laws apply? If a crew member demands to be euthanized because they are suffering from an agonizing, untreatable radiation cancer, who makes that horrific moral decision? There are absolutely no space laws written for these grim, inevitable realities. Economically, a manned mission to Mars requires a scale of investment that borders on the absurd. Estimates range from hundreds of billions to over $1 trillion. The Apollo program cost roughly $150 billion in modern currency, and it only went to the moon for a few days. The International Space Station cost over $150 billion to build and maintain in low Earth orbit. A Mars mission requires entirely new classes of super heavy lift rockets, deep space transit habitats, untested landing modules, autonomous fuel plants, and revolutionary life support systems. While private companies boast about rapidly lowering the cost of spaceflight, their financial models often rely on highly optimistic, unproven assumptions about continuous, exponential technological growth. There is absolutely no immediate economic return on a Mars mission. You cannot mine heavy metals and ship them back to Earth profitably. There is no strategic military advantage. The romantic idea of Mars serving as a backup planet for humanity in case of a global catastrophe is deeply, fundamentally flawed. Even if Earth were devastated by a massive nuclear war, struck by a dinosaur-killing asteroid, and ravaged by a global pandemic, all at the same exact time, the smoking, irradiated ruins of Earth would still be infinitely more habitable, warmer and richer in breathable oxygen and water than the absolute best day on Mars. Maintaining a fragile colony on Mars would require a massive continuous lifeline of supply ships from Earth for centuries. If Earth falls, the Mars colony will quake, starve and suffocate in the dark. Ultimately, the overwhelming, undeniable combination of all these factors, the invisible fire of radiation, the bone-dissolving microgravity, the mind-breaking psychological isolation, the statistical certainty of mechanical failure, the inability to provide medical care, and the absolute impossibility of an emergency rescue creates a grim, inescapable reality. The probability of the first manned crew dying in the cold dark is significantly, undeniably higher than the probability of their safe return. This is not pessimism, it is the cold, hard mathematics of survival in an environment that actively wants to kill you. The history of human exploration is indeed built on the bones of brave pioneers. The Franklin expedition completely vanished in the ice. Scott and his men froze to death at the South Pole. But there is a massive, fundamental difference between those historical tragedies and a modern Mars mission. Those early explorers faced unknown, unquantifiable risks, hoping for a bit of luck. The astronauts who go to Mars will know exactly, scientifically, how high the probability of their agonizing death is. They will be walking into a highly predictable, technologically complex meat grinder. The ethical implications are staggering. Is it morally acceptable for society, for governments, or for private billionaires to send human beings on a mission where a horrific death is the most statistically probable outcome? The technological development required to make a Mars mission truly safe, not just a suicide run, will likely take many decades, perhaps an entire century. We need revolutionary breakthroughs in autonomous artificial intelligence, closed-loop life support, advanced propulsion, and radiation shielding. These miracles of engineering cannot be rushed by sheer political willpower or corporate marketing. The universe is governed by the absolute laws of physics, and physics does not care about human ambition or the desire for a good television broadcast. The robotic probes and rovers are doing incredible, profound scientific work right now, expanding our knowledge of the cosmos without risking a single human life. When the first human beings eventually do depart for the Red Planet, whether it is in 10 years, 50 years, or a century from now, they will know exactly what they are walking into. They will know about the radiation tearing through their DNA, the muscles wasting away, the creeping madness of isolation, and the terrifying silence of an unbreakable communication delay. They will accept these horrific risks, and their immense bravery will demand our absolute respect. But our deep respect for their courage must not blind us to the moral responsibility of sending them. We must not send them before the technology is truly ready. We must not sacrifice brilliant human lives on the altar of premature ambition or corporate pride. Understanding our limitations is not a defeat. It is the ultimate manifestation of scientific maturity. Acknowledging the extreme, deadly risks is not cowardice. It is cold, necessary rationality. The Red Planet has existed for billions of years, a silent, rusty jewel in the dark. It is not going anywhere. It will wait for us. A delay of a few decades is absolutely nothing in the grand scale of cosmic time, but it could mean the difference between a triumphant new chapter in human history and a dark, televised tragedy that halts space exploration for a generation. The first humans to walk on Mars deserve a mission that is a beginning, not a terrifying, predictable end. The decisions we make today will determine whether Mars becomes a monument to human ingenuity or a highly expensive, frozen graveyard in the deep dark. Sleep well, keep looking up at the sky, and never ever stop completely wondering about the vast, terrifying, and endlessly beautiful universe we call our permanent only home.